July 1st, 2025, Chile. The Atlas telescope at Rio Hurtado scans the border between Serpens Cauda and Sagittarius. 4 30-second exposures in O-band filter. Magnitude 18, moving fast. The Atlas survey logs it as candidate A, 11PL3Z at 05:15:11 Universal Time. Within hours, amateur astronomer Sam Dean checks older frames from the same system. There it is on June 5th, June 25th. Crossing the densest star fields near the galactic center, dense enough that automated detection algorithms couldn't separate the comet from background stars. That's why nobody saw it earlier. The object was hiding in plain sight against a wall of stars. Not invisible, just camouflaged. Initial trajectory shows hyperbolic, not bound to the sun, speed 61 kilometers per second relative to our star. Located 3.5 astronomical units from Earth, 4.51 AU from the sun. This is not ours. 3 arc-second tail-like elongation. Marginal coma visible. Lowell Discovery Telescope in Arizona sees the same. Deep Random Survey in Chile confirms. Not an asteroid, a comet, active, outgassing. By the time the Minor Planet Center officially announces 3I Atlas on July 2nd, they've collected 122 observations from 31 different observatories. The designation is clear, 3I, third interstellar object. Atlas for the survey that found it. The comet also gets designation C 2025 N1, non-periodic comet, never coming back. This script is researched and factual using sources from the European Space Agency's official planetary defense reports published November 14, 2025, and NASA's comet tracking data released through the Minor Planet Center database. We're pulling from ESA's Near-Earth Object Coordination Center and peer-reviewed studies and monthly notices of the Royal Astronomical Society. Now back to the information. The comet enters at 4.51 astronomical units from the Sun, 325 million miles from Earth. Its trajectory screams interstellar. Follow the path backward, and it points to either the Milky Way's thin disk or thick disk. If it came from the thick disk, the comet could be 7 billion years old, older than the solar system itself, older than Earth by 2.5 billion years. This thing witnessed the universe when it was less than half its current age. But here's the immediate problem. It's moving at 245,000 kilometers per hour through our system. Speeds like that don't give you time. You track it now or you lose it forever. By July 21st, Hubble locks on, 277 million miles out. The image shows a teardrop-shaped cocoon of dust. The nucleus sits somewhere inside. Estimates put it between 440 meters and 5.6 kilometers across. That's a massive range. The uncertainty is real. David Jewett and Jane Liu at the Nordic Optical Telescope confirm it's clearly active on July 2nd. Diffuse appearance, a coma forming. This is a comet, not an asteroid. Not. More frames from May 21st at Weizmann Astrophysical Observatory in Israel. NASA's Transiting Exoplanet Survey satellite catches it even earlier, May 7th through June 3rd. 6.4 astronomical units from the Sun and already active. Water ice doesn't sublimate at that distance. Freezing point too high. This means carbon dioxide, carbon monoxide, volatiles that turn to gas in deep cold. Temperatures where water stays frozen solid. The coma grows fast. By July 3rd at Gran Telescopio Canarias, high-resolution images measured 26,400 by 24,700 kilometers, twice Earth's diameter. Elliptical shape, slightly elongated, dust production increasing daily. Nordic Optical Telescope does the same. Reflectance spectra show slight reddening. 400 to 700 nanometers, wavelengths covering blue through red visible light. Spectral slope measures 22.8 plus or minus 0.1% per micrometer. That reddening indicates organic-rich materials. Carbon chains, tholins possibly, complex organics formed by radiation processing. Similar to what we see in outer solar system objects. Kuiper belt, scattered disk, but not identical. Subtle differences in the slope. Variations in absorption features. Strong absorption bands at 4.26 microns. Water vapor present, but weak. 1.4 and 2.7 micron bands barely detectable. Traces of nickel compounds. Organic signatures, not common in solar system comets. The chemistry screams alien. Webb calculates ratios. Carbon dioxide to water, 8 to 1. Among the highest ever measured. Most comets show the opposite. Water dominant by factors of 10 or more. 3I Atlas flips that script. Whatever system it formed in had abundant carbon dioxide ice, limited water, temperature regime colder than our protoplanetary disk, or formation location farther from the parent star, or parent star chemistry different from the Sun. CN emission lines at 388 nanometers. Classic comet signature means carbon and nitrogen chemistry active in the coma. photodissociation breaking down parent molecules. July 20th, VLT finds atomic nickel vapor using X-shooter instrument. Emission line at 352.45 nanometers. Nickel is rare in cometary spectra, but not unknown. Found in solar system comets at parts per billion. 3. iAtlas shows higher abundance, parts per million range. Either the parent body is nickel-rich, or sublimation processes differ. 20 times weaker than carbon dioxide lines. Normally water dominates by that factor. Everything is inverted. Tony Santana-Ross publishes analysis in August. Coma became redder throughout July, evolving color. Surface, or coma composition, changing as the comet approaches the sun. Increasing cometary activity releasing fresh material. Pristine ices exposed. Radiation processed mantles sublimating away. Each layer tells a story. Each spectral shift reveals formation history. But there's a ceiling. Earth-based telescopes can only do so much. Parallax from a single planet limits precision. You're looking at the comet from one angle, one location. The uncertainty in its predicted path stays wide enough that aiming instruments becomes guesswork. For a comet racing at 250,000 kilometers per hour, every kilometer of error compounds. Miss your window and the data is gone. Then someone at ESA's Planetary Defense Office has an idea. Mars. The geometry is perfect. Detecting seasonal variations, its color and stereo surface imaging system was built to map surface features in high resolution. 4.6 meters per pixel from 400 kilometers altitude. Point it down at craters and valleys, dunes and layered deposits. Never meant for deep space. But between October 1st and October 7th, 2025, the spacecraft does something it was never designed to do. It points up, away from Mars. At the sky, at 3 iAtlas sweeping past. From Earth 3, iAtlas shines at magnitude 17 to 18. From Mars, it's magnitude 14 to 15. Nearly 10 times brighter, angular size larger. Details visible that Earth can't resolve. But distance alone isn't the prize. It's the angle, the viewing geometry. Earth sees the comet from one side of the solar system, Mars from another. Baseline between observation points measured in astronomical units. Parallax enormous. Triangulation potential massive. They calculate new exposure times, long enough to capture faint comet signal, short enough to avoid saturation from bright stars in the field. They adjust gain. They reprogram pointing sequences. They account for the spacecraft's orbital velocity around Mars, 4.2 kilometers per second at apoapsis. Account for Mars's position relative to Earth and the Sun, Mars orbital velocity 24 kilometers per second. Account for the comet's hyperbolic trajectory and the exact timestamp of each observation. Comet moving 50 kilometers per second in inertial frame. Their positions known from telemetry. Ephemeris predictable. Models validated over decades. Never a spacecraft orbiting another planet. Never Mars. The challenges pile up fast. Flight dynamics teams coordinate with instrument teams coordinate with science teams. Calculate TGO position at each exposure instant. Not just orbital elements, actual position in J2000 coordinates. Propagate forward from last ranging measurement. Account for atmospheric drag, negligible at 20,000 kilometers, but still there. Account for solar radiation pressure. Photons pushing on solar panels. Account for gravity harmonics. Mars isn't a perfect sphere. Mass distribution uneven. Olympus Mons, Hellas Basin, Tharsis, Bulge, all tug differently. Every perturbation accounted for. Margins that are normally negligible now matter. Every pixel counts, every timing adjustment. They reduce the error as far as the math allows. The comet moves relative to those fixed points. Measure its position in each frame. Correct for spacecraft motion, correct for light travel time. Photons took 97 seconds to reach TGO from the comet at closest approach. Comet moved 5,000 kilometers during that time. Correct for relativistic effects. Spacecraft velocity approaching 100% of light speed. Time dilation negligible, but aberration matters. Apparent position shifts by microarc seconds. Factor it in. Factor of 10. ESA announces it November 14th, 2025. The comet's predicted location now 10 times more accurate than before. The uncertainty that plagued every telescope pointing is slashed. This is the first time astrometric measurements from a spacecraft orbiting another planet have been officially submitted and accepted into the Minor Planet Center database. The database that tracks every asteroid and comet observation worldwide. Ground telescopes, radar stations, spacecraft, all feeding into one clearinghouse. And now Mars-based data sits in that archive. This research is backed by ESA's official November 14th announcement and tracking data published through phys.org and Universe Today on November 15th and 16th. The Minor Planet Center confirms acceptance of the Mars Orbiter Astrometry in their public database. Now back to the story. Closest approach. December 19th, 2025 at 270 million kilometers, 1.8 astronomical units, almost twice the Earth-Sun distance, safe. But the exercise is a rehearsal. ESA routinely monitors near-Earth asteroids and comets, calculating orbits, issuing warnings when required. This rehearsal with 3-eye atlas shows what's possible when you triangulate Earth data with observations from a second location in space, especially when that second location is closer to the object. Adds value, real operational value. Practicing with spacecraft data beyond Earth, orbit hones skills. It demonstrates you can leverage resources not designed for asteroid detection. Boosts readiness for an actual threat. Richard Moisel heads the Planetary Defense Office at ESA. He explains the precision gain. Looking at the comet from a very different point in the solar system and combining measurements taken from Earth increases knowledge about position at a specific time significantly. With that data, the future path can be determined much more precisely. The comet has passed closest approach to the Sun, starting to leave the solar system. Visible again from Earth in December. Even after closest approach to Earth, still 1.8 times farther than the Sun, it will be observable for several months. As long as the comet can be observed, there are opportunities to study the evolution of the coma, the envelope of gas dust and larger pieces lifted off by evaporation. Mars Express also observes, but exposure times are too short. The comet doesn't show in those frames. NASA's Mars Reconnaissance Orbiter captures data, but NASA faces a government shutdown. The data stays unreleased. China's Tianwen-1 orbiter images it. Multiple spacecraft, multiple nations, all eyes on this visitor. September 16th, NASA's Lucy mission catches 3-eye atlas at 45 million kilometers. The spacecraft wasn't designed for comet intercepts, still made the observation. November brings another player, ESA's Jupiter Icy Moons Explorer, JUICE, en route to the Jovian system, farther from 3-eye atlas than the Mars orbiters were, but timing is perfect. Just after the comet's closest approach to the Sun on October 29th, perihelion at 1.36 astronomical units, 203 million kilometers, between Earth and Mars. JUICE sees the comet in its most active state, bright halo around the nucleus, long tail stretching behind. JUICE uses cameras, spectrometers, and a particle sensor, but thermal conditions are brutal. The spacecraft is traveling through the inner solar system. High-gain antenna used as a heat shield, data transmission drops to a crawl through the medium-gain antenna. The observations won't reach Earth until February 2026, or it forms so far out in its home system that only the most volatile ice is condensed. Temperature regimes we don't see in our own Kuiper belt or Oort cloud. The organic signatures add another layer. Spectra from salt and not show reddening in the optical range, 400 to 700 nanometers. Spectral slope 22.8% per micrometer. That indicates organic-rich materials. Similar to outer solar system comets, but not identical. The chemistry suggests this object has been wandering interstellar space for millions of years, maybe hundreds of millions. Cosmic radiation alters ice chemistry over those timescales, produces physical behaviors distinct from native solar system bodies. Rotation consistent with active comets in our system. Dust activity increased through July. Mass loss rates between 0.3 and 4.2 kilograms per second. Weakly active for something so far from the Sun, but active nonetheless. No visible tail during observation periods. Viewing geometry and low dust production explain that. The coma remains predominantly asymmetric. No fragmentation, no rapid changes. The nucleus holds together, large dust grains, less affected by solar radiation pressure. They stay near the nucleus instead of streaming away. 77,132 stars with full three-dimensional velocity data. 3-eye atlas aligns with disk kinematics. If from the thick disk it traveled for at least 7 billion years, formed when the universe was 7 billion years old, witnessed cosmic noon, the era of peak star formation, the era when galaxies were building. If from the thin disk it's younger, still ancient. Still carrying chemistry from another stellar neighborhood. This is when Mars orbiters and JUICE observations matter most. They fill the gap. October 31st, Earth-based astrometry resumes. The comet emerges from behind the Sun, still visible with small telescopes in the pre-dawn sky. December 19th, closest approach to Earth, 270 million kilometers. Telescopes will aim with confidence thanks to the refined trajectory. After that, 3-eye atlas continues outbound. March 16th, 2026, close encounter with Jupiter. Orbit dynamicists will watch for tiny deviations. Non-gravitational acceleration from outgassing acts like microthrusters alters the path subtly. Those deviations refine models further. Then the comet fades, heading toward Gemini, back to interstellar space, never to return. A spacecraft positioned at Lagrange point 1, between Sun and Earth, 1.5 million kilometers sunward from Earth, monitoring the blind spot, the zone where asteroids approach from the sun's glare. Current telescopes can't see there. Too bright. By the time an object emerges from glare, it might be days from impact. Not enough warning. Neomir changes that. Infrared sensor, heat signature detection, doesn't need reflected sunlight. Can see objects coming from the sun's direction, detects them weeks in advance. 3 weeks minimum for potential impacts. Enough time to calculate trajectory. Enough time to decide on response. Enough time to warn populations if needed. Launch planned for 2031. 1.5 million kilometers anti-sunward from Earth. Waiting. Not aimed at any specific target, armed instead with fast response capability when a new comet appears, long period or interstellar. The spacecraft deploys. 3 components. Main craft plus 2 subprobes. Intercept trajectory calculated. Delta V budget, 900 meters per second. Enough to reach targets discovered with months of lead time. Flyby speed, adjustable. Close approach distance tailored to target activity. Instruments designed for dust analysis, gas composition, nucleus imaging, magnetic field measurements, plasma environment. All the data we couldn't get from 3i Atlas because it moved too fast and we had no dedicated spacecraft ready. Next time will be different. Comet Interceptor will be waiting. If another ISO appears, with 4 to 6 months lead time, the spacecraft can reach it. Study it up close. Capture measurements impossible from Earth or Mars orbit. That's the goal. Turn interstellar visitors from observational targets into laboratory subjects. Space telescopes. The response was immediate, but gaps exist. Southern Hemisphere has better coverage than Northern. Certain longitude ranges lack major facilities. Cloudy weather grounds, optical telescopes. Radio telescopes help, but infrared and UV require space-based platforms. Building redundancy matters. More facilities, more wavelengths, more platforms. The Rubin Observatory comes online soon. Vera C. Rubin Observatory in Chile. 8.4 meter primary mirror, 3.2 gigapixel camera, widest field of view of any large telescope, 10 square degrees per exposure, entire visible sky every 3 nights. Projections estimate dozens to hundreds of interstellar objects during its first decade of operation. Statistical studies become possible. Frequency of ISOs, size distribution, composition trends, dynamical origins, cluster ISOs by galactic source region, map out which parts of the galaxy send more visitors, understand ejection mechanisms, how many from thick disk, how many from thin disk, how many from halo. Statistical samples transform ISOs from rare curiosities into regular tools for understanding planetary system formation across the galaxy. 3i Atlas is data point 3. Rubin will deliver data points 4 through 100 in the next 10 years. The field explodes. The Mars orbiter breakthrough changes the game. For decades, trajectory observations relied on Earth's surface or near-Earth orbit. Fixed geometry, limited parallax. Now planetary missions become mobile observatories. A spacecraft at Mars, another at Jupiter, eventually one at Saturn or beyond. Each position adds an observation angle, triangulation across the solar system. Precision increases with distance between observers. For an object traveling 250,000 kilometers per hour, precision matters. Miss by 1 hour and you miss by 250,000 kilometers. The refined trajectory from TGO cut that error by 90%. Future threats will benefit from this technique. The clearest image captured October 2nd when 3i Atlas passed Mars, 30 million kilometers. He dismisses alien speculation but points to missed scientific opportunity. Terrestrial stupidity, not extraterrestrial intelligence. His remarks highlight ongoing debates about data access, how space agencies handle public information on rare interstellar visitors. The scientific community wants open data streams, real-time access to observations. Some agencies comply, others lag behind. 3i Atlas became a test case, not just for tracking, but for transparency. If another ISO appears and we want to send a probe size, estimates need to tighten. Close flyby missions require knowing the nucleus dimensions, the dust environment, the outgassing rates. 3i Atlas showed we can track path precisely, but physical characterization still needs work. Multiple wavelengths, multiple observation phases, pre-perihelion, perihelion, post-perihelion. Each phase reveals different aspects. JWST captured infrared spectra. Hubble captured optical images. Swift Observatory found tentative water vapor in OH. VLT detected cyanide and nickel. TESS caught early activity. Vera Rubin imaged it during science validation June 21st through July 3rd. Each instrument added a piece. The full picture requires all of them. Successfully detected 3i Atlas using image stacking. Rapid motion compensated through multiple exposures. Brightness measurements showed steep increase, consistent with dynamic new comets on first close approach to a star. sublimation of unaltered volatiles, primordial interstellar materials preserved since formation. Radio observations began July 2nd at SETI Institute's Allen Telescope Array, targeting narrowband emissions. Potential technosignatures and natural emissions, continuum radiation from dust, spectral lines from molecules like hydroxyl. The search for artificial signals came up empty. 3I Atlas behaves like a comet. Natural, not engineered. But the protocol was followed. Every interstellar object gets checked, just in case. But showed significant non-gravitational acceleration. Debate raged over whether it was a comet or something else. Hydrogen iceberg hypothesis. Alien light sail speculation. Still unresolved. 2I Borisov, 2019. Clearly a comet. Active coma, extended tail. Composition similar to solar system comets. Water-rich. Behaved exactly as expected. 3I Atlas falls between them. Active like Borisov, but with alien chemistry. Carbon dioxide rich, water poor. Organic materials with unusual spectral slopes. It's a comet, but from a place where comet building blocks differ from ours. December 19th, closest approach provides prime opportunity. Hubble, JWST, large ground telescopes, high signal to noise images and spectra. NASA and ESA will release summary reports on chemistry and jet behavior. 16 March 2026, Jupiter encounter, final milestone before 3, Atlas vanishes forever. Separated by at most 12,700 kilometers, Earth's diameter. That parallax helps, but it's limited. Mars orbits 142 million kilometers farther from the Sun than Earth on average. During October 3, Atlas was positioned, so Mars offered a baseline millions of kilometers different from Earth's perspective. TGO orbiting Mars added another variable. The spacecraft moves around Mars at several kilometers per second. Exact position at each observation instant mattered. Flight dynamics teams calculated TGO's location to meter scale precision, combined that with comet position in the frame. Stellar background provided reference points, stars whose positions are known to Milliarc's second precision from Gaia. The comet moved against those stars, measure its position relative to stars. Correct for TGO's motion, correct for Mars's motion. Triangulate with Earth observations, corrected for Earth's rotation and orbit. The math is brutal, but it works. Became the first Mars orbiter astrometry in the MPC archives. Sets precedent. Future planetary missions can now submit observations knowing the protocol exists. NASA's Psyche mission also measured 3I Atlas, data pending. ESA's JUICE has measurements scheduled. Low transmission rate delays receipt, but the framework is proven. Planetary missions are now part of the asteroid and comet tracking network. Not every spacecraft can divert to observe passing objects. Primary missions take priority. Instrument pointing, data storage, transmission bandwidth, fuel for maneuvers, all limited resources. 3I Atlas got lucky. Multiple spacecraft happened to be positioned favorably. Mars orbiters, JUICE heading toward Jupiter, Lucy in the asteroid belt, Psyche en route to its target. Europa Clipper potentially immersed in the ion tail October 30th through November 6th. Hera possibly in the tail October 25th through November 1st. Opportunistic observations, not planned intercepts. Next time might be different. An ISO might pass when no spacecraft are positioned well, or when spacecraft are in critical mission phases and can't divert. Building dedicated ISO intercept capability requires different mission architecture. Comet Interceptor is one approach, parked at Lagrange Point, waiting, ready to deploy when a target appears. Response time measured in months if the target is discovered early enough. 3I Atlas was discovered 4 months before perihelion, enough time for a prepared mission to reach it, but launching after discovery is harder, requires massive delta V. Yaganuma's study calculated over 24 kilometers per second for post-discovery Earth launch, beyond current propulsion systems. Mars launch would require 5 kilometers per second between July and September, more feasible but still a stretch. Isotope ratios, dust grain properties, organic complexity, questions about life's building blocks. Are they universal? Do all systems produce similar organics, or is Earth's chemistry unique? 3I Atlas shows at least one other system produces complex organics. The spectral signature is there, reddish color and optical range, similar to outer solar system comets but distinct, formed under different temperature pressure conditions. Maybe different stellar metallicity, maybe different time scales. 7 billion years in interstellar space changes things. Cosmic rays strip surfaces, alter ice structures, create radiation-damaged layers. What we see now might not match what formed initially. Thin disk stars are younger, 1 to 7 billion years. Either way, the comet is ancient, formed in the early universe, cosmic noon, peak star and planet formation, galaxies colliding and merging, gas flows fueling massive starbirth, planets forming in those disks, comets forming in those outer regions, some ejected by giant planets, sent into interstellar space, wandering for billions of years until chance brings them near another star. One in however many trillion comets ever formed. We happen to be here with telescopes when 3I Atlas passes through. For a comet moving as fast as 3I Atlas, that translates to much better predictions, days and weeks ahead. Telescopes can be scheduled with confidence, exposure times optimized, spectroscopy planned, photometry campaigns coordinated, all because the trajectory is nailed down. Without Mars, data astronomers would still be guessing. Wide error ellipses, instruments aimed at empty space, data quality suffering, science lost. The technique generalizes. Any fast-moving object benefits from multiple observation points. Near Earth, asteroids traveling close and fast, long-period comets on first visit, interstellar objects, even artificial satellites re-entering. If you can observe from two widely separated locations, triangulation improves precision. Earth and Moon, Earth and Mars, Earth and Jupiter. The farther apart, the better. As human presence spreads through the solar system, observational capabilities multiply. A telescope on the Moon gives you Earth-Moon baseline, 380,000 kilometers. A telescope on Mars gives you Earth-Mars baseline, hundreds of millions of kilometers. A telescope in the outer system gives you baselines measured in astronomical units, precision scales with baseline. For objects at interstellar distances, even 1 AU separation yields measurable parallax. Decision-making under uncertainty matters. Knowing when to push instruments beyond design specs matters. TGO was never meant to image distant comets, but it did, successfully, because the team figured out how. That knowledge stays. Next time is easier. Is it dangerous? No. Where did it come from? Another star system. Can we visit it? Not this one. Too fast. Too far. But maybe next time. Maybe with Comet Interceptor. Maybe with a mission we haven't thought of yet. Public interest drives funding. Funding drives missions. Missions drive discovery. The cycle continues. Each ISO raises the profile, makes the next mission easier to justify. 3I Atlas is the third. There will be a fourth, a fifth. Eventually they'll be routine. We'll study them the way we study asteroids and comets now. Sample return missions. In situ analysis, chemistry, mineralogy, age dating, isotopes, building a library of interstellar materials, understanding how planet formation varies across the galaxy. Suggested artificial origin. The community pushed back. Galactic velocity vectors have distributions, some align with ecliptic by chance. Not evidence of engineering, just statistics. Run the numbers. Thousands of ISOs pass through the galaxy. Some fraction intersect the solar system. Of those, some fraction happen to align with ecliptic. 3I Atlas is one. Natural selection bias. We detect objects on ecliptic plane more easily. Survey telescopes scan that region more often. Detection probability higher. Apparent alignment reflects observational bias, not artificial steering. The chemistry clinches it. Carbon dioxide, cyanide, nickel, water ice, dust. All natural comet stuff, just in different proportions. Natural origin, no question. JUICE data arrives February 2026. Analysis will continue for years. Papers will be published, conferences will dissect every detail. But the operational breakthrough is already locked in. ESA proved you can refine an interstellar object's trajectory using Mars orbiter data. Factor of 10 improvement. First, Mars-based astrometry in the Minor Planet Center database. First, planetary defense triangulation rehearsal using off-planet assets. The technique works. The precedent is set. The next ISO will be tracked even better. And the one after that, better still. Each iteration sharpens the tools. Each visitor teaches new lessons. 3I Atlas is teaching us now. The lesson is clear. When you need precision, look from multiple angles. When you need accuracy, go off-planet. When you need to protect Earth, use every resource you have, even ones designed for other purposes, even ones orbiting other worlds. Until chance brings it near another star, another civilization. If they're watching, if they have telescopes, if they care about visitors from the void, they'll see what we saw. A chunk of ice and rock and organics, a time capsule from another era, a messenger from the ancient universe, carrying chemistry that formed when galaxies were young, when stars were being born in massive nurseries, when planets were just beginning to coalesce. 3. I-Atlas is a survivor, an artifact, a window to processes we can only glimpse in our own backyard. And thanks to a camera on a spacecraft orbiting Mars, that camera designed to photograph rocks and dunes and craters, instead pointed at the sky for 7 days. In October, we now know exactly where that window is, exactly where to look, exactly what we're seeing. The error bars are tight, the data is solid, the message is received. That's what ESA delivered. That's what the Mars data revealed. Not just a trajectory, but proof that when the stakes are high and the target is fleeting and the clock is ticking, we can adapt. We can innovate. We can turn a geology camera into a comet tracker. We can combine observations from 2 planets and 6 spacecraft and 100 ground telescopes into one unified solution. We can cut the uncertainty by 90%. We can nail the path. We can predict the future with confidence. And when the next visitor arrives, racing in from the stars at speeds that would shame any comet we've ever seen, we'll be ready. We'll have the tools, we'll have the techniques, we'll have the experience. 3i Atlas gave us that. Not in danger, just in preparation. The rehearsal paid off. The test case worked. Planetary defense leveled up.